Okay, this is almost one. But as a function of the streaming energy, these are the curves, and that depends on the dielectric constant, and that value from the most value to this one. The value used by Optimal is not suitable. We feel that this is bad. And one more slide. That a plot of this for various values of n, the effective mass equals 5 times, 10 times, 15 times. So you can increase and we find that when cleaning energy he quoted for palladium 250 electron volts. You also quoted for palladium oxide 600. So I don't know, but I didn't plot because we have to discuss that experiment whether that is achievable or not. But if there are non-metallic systems, I believe the screening energy is much more, which is reducing to the values. When you learn more somehow. So then the value, effective value of the mass, electronic mass, the mass share of electrons is much higher. So this shows that this mechanism can explain quite a few results.
That's not a problem. It's very good. Okay, we don't have any time for questions. So, the next speaker is somebody on my life called Chubb. The requirement reads
copy of it.
That's all right, don't worry about it.
Don't come apart.
On that screen. Okay. All right. Okay.
Well, this talk concerns the quantum physics underpinning of radiationless deuterium fusion. Quantum physics teaches us that all matter is quantized, which means that the least massive portion of any pure substance has a specifiable discrete value of mass, charge, and spin. However, these minimal portions are not always particle-like. We typically think of them as localized and call them particles, for example, atoms, molecules, and nuclei. But the minimal portions can also be delocalized as wave-like, as in Bose-Einstein condensates, the electron pair MEC, and other so-called quantum fluids. In the delocalized state, they usually share the same volume with like entities, merging with them so as to resemble a continuous, undifferentiated medium. Such an undifferentiated medium typically exists in a simple, single-volume potential well, as in most of the Bose-Einstein condensate experiments. However, quantum fluids can also exist partitioned into separate volumes inside separate potential wells, such as occurs in Bose-Einstein condensates in optical lattices. And also electrons in the electron pair MEC. Radiationless cold fusion requires delocalized, partitioned, overlapping flattening product of nuclear matter coupled to a dissipated medium. And this is the essence of this view graph here, because it really, the whole point really is that you get fusion without any radiation. This is the only way that these are the conditions that are required, as far as I can see anyway. Now, with this picture in mind, we can define some of the experimental requirements for achieving radiationless deuterium fusion. We must create structures which act as hosts for delocalized partition deuteriums. We must provide deuterium flows such that fluxing deuteriums will overlap and resonate with bound D+ block states of the host lattice. And there must be a coupling between nuclear changes and an overlapping dissipative medium. Now, one such dissipative medium are the electrons in the middle, and it seems like this last condition is probably automatically met when the host lattice is a metal. Now, I want to talk about various types of overlap and the way nature responds to the Coulomb repulses of pairs particles. We have mentioned the requirement for deuteron-deuteron overlap. In general, there are two ways by which charged particle pairs can have mutual particle-particle overlap. One way is illustrated by what happens in muon-catalyzed deuteron fusion. When negative muons are allowed to thermalize inside a deuteron-containing medium, ED mu- molecules form. These muonic molecules are 500 times smaller than normal D2 molecules. And this treatment this type of fusion was analyzed by Jackson back in 1957. There's tunneling when you have these very small molecules, 500 times smaller than a chemical D2 molecule or a D2 plus molecule. You get basically the same physics that goes as with any kind of a molecule. But they're so close that you get significant tunneling from one deuteron into another. What you have is the rate, basically, of muon-catalyzed fusions in terms of the two-particle wave function evaluated at zero separation. And this is basically the equation that the physics that Jackson used in 1957. However, this type of fusion cannot be involved in Fleischmann-Pons type fusion because this is always accompanied by radiation, the normal helium-3 neutrons or the tritium proton and high energy emission. But there is a second response which nature makes to adjust the particle-particle Coulomb repulsion. It is a response which nature chooses if the mutual Coulombic repulsion is not too large. The second response is illustrated by what happens between the two electrons of the helium atom. In the ground state helium atom, the electron charge distribution is strictly radial, despite the mutual repulsion intrinsic in the electron pair. Radial symmetry means that the two electrons have mutual wave function overlap. If the charge of the electron were vanishingly weak, this electron-electron overlap would be 100%. Both electrons would have exactly the same radial distributions at all times. But with electron charge at nature's value, the overlap is about 70%, which means that there is a measure of correlation avoidance between the two electrons. This correlation avoidance does not affect the spherical symmetry of the system, but it reduces the overlap below 100%. This is the Hilbert simplest approximation. Two-particle wave function is written as a product, or can be written as a product, of a distribution in physical space times distribution in parameter space. This is basically a six-dimensional wave equation for two particles. And this is a radial distribution which fits a helium atom, more or less like the hydrogen atom. This is something which modulates that distribution, depends on the vector separation of the two electrons. Okay, so that leads us to the point, when does nature choose correlation avoidance as its response to Coulomb repulsion or between a pair of particles over the side-by-side paired particle molecule type configuration? Nature's choice is determined by system energy minimization. It is determined by three factors: the mass of the paired particle, the strength of the point particle Coulomb repulsion, and the unit cell size of the host lattice, which for metals is determined by the electron de Broglie wavelength. Now, low particle mass, weak Coulombic repulsion, and small lattice constant favor the correlation avoidance configuration, which preserves a simpler symmetry. So now we come to the crux of the radiationless deuteron fusion process. There is a form of deuterons on metal surfaces and inside metals that shares the symmetry of the metal lattice and it permits deuteron pairings while preserving lattice symmetry, just like the helium solution preserves radial symmetry here. The wave functions of such deuterons are block functions. Block function deuteron quantum fluids have been observed on the surfaces of metals by Pushka et al. And Estaldi et al. In papers published in Physical Review Letters. The conditions for deuteron pairing without breaking periodic symmetry is met if the number of unit cells over which the block function configuration is valid exceeds something like n cell. There must be fully coherent deuteron behavior over the m cell unit cells. This is to say that as far as the deuterons are concerned, each of the n cell unit cells is equivalent, and each portion of each of the partition block deuterons behaves coherently. That is, moves in lockstep. Well, basically, the equivalence of each unit cells is the principle which Bloch initiated many years ago. The net result is that the point particle dd Coulomb repulsion is reduced by a factor of n cell. The reduced dd repulsion makes the correlation avoidance configuration the energy minimizing system configuration when you have large coherent volumes. The quantum physics of block function pairs with correlation avoidance is illustrated by the two deuteron wave function describing paired deuterons. This next chart is a line chart showing the two-particle wave function. Again, just as in the Hiller solution for the helium atom, it's written as a product of a distribution in physical space times a function of parameter space. And in physical space, what we have done is the wave function gives you this part of the wave function gives you the amplitude of the charge throughout the coherent volume of the crystal. And if you take a particular line through the crystal that goes through the center of the potential wells and across saddle points between the wells, you get a series of maxima in each of the potential wells. And the other part of this six-dimensional wave function is the dimming function, again like in the Hiller solution. And the whole point is if you apply strict periodic symmetry to this problem, both of these functions are block functions with independent Bravais lattice vectors. And these points are the points where in each unit cell where the point characteristic of the charge coincides. Okay. So the net result of this is that the point particle, well, I've said that before. Because of a coherency, when you calculate the repulsion of effective repulsion, Coulomb repulsion for this system, you have to add up the repulsion in each of the n cells. So you have n cell times the repulsion of potential that's in each of the unit cells. But because of the partition of each of these particles in this block function configuration, each unit cell contains only a 1 over n cell fraction of each deuteron's point's charge. And you apply the 1 over n cell squared times n cell, that leaves you the 1 over n cell effective repulsion for the particle as a whole. Now, how much time do we have? Philip Anderson has emphasized the importance of symmetry in separating the different regimes of physical behavior characterizing the separate sciences. Radiationless cold fusion belongs to the discipline of lattice physics, where periodic symmetry is preserved, rather than to the discipline of chemistry. Nonetheless, the problems associated with realizing practical radiationless deuteron fusion seem to belong to chemistry. It is to be hoped that this mixing of disciplines will not slow down the development of practical cold fusion heat devices.
Okay, we don't really have time to, unless there's a quick question. I want to make a comment that he's showing cusps. Those cusps in the separation variable correspond to the points in the muffin fins where I was saying you do the matching of the nuclear wave function. Other comment is that when you minimize the energy, that's equivalent to going to a very, very slow rate of reaction. Minimizing the energy means you're in an eigenstate, you're going to an eigenstate type of configuration. That was embodied in some of the rate expressions. Peter Hagelstein, again, I apologize. Actually, it's sort of neat. He's got double exclamation points. His affiliation is MIT, so that's nice. Anyhow, Peter Hagelstein from MIT.
Okay, I'm interested in a model for fast ion emission. Some years ago, experiments were done with metal deuterides, and a variety of results gave fast ions coming out at the end of the level. In two cases, they were measured with a suitable detector, and only recently has it become clear what the origin of it is. So I'm going to talk about a new model for interaction of the lattice and nuclei, conjecture, coherent part of interaction, and so forth. So, theory talk. I've been interested in anomalies and metal deuterides for some time, and I've looked at a large number of models for trying to figure out what's going on. The model I'm looking at these days has 5 parts to it, 3 quantum systems and 2 interactions. Quantum systems are a nuclear quantum system, which is deuterons either in atomic states or bound together in a helium state. The lattice phonons and dissipation mechanisms. I'm going to couple the nuclei to the phonons and the phonons to a dissipation system. To some degree, similar in flavor to what Talbot was talking about initially. The models for the basic quantum system, I'm just using a pseudo-spin description. So I have deuterons as deuterons, and then I have deuterons as nuclei. For phonons, I'm using multi-phonon lattice model. For dissipation channel, I'm using here a generic dissipation channel, and I have the freedom to pick them to be electron excitation, phonon production, or other channels if I can think of some. The basic interactions are as follows. For the nuclear phonon coupling, the basic idea is that if 2 deuterons are apart, they don't interact. If they come together, they have the possibility for interacting. So the interaction with the phonons comes about in this model through the highly nonlinear problem getting them close together. I have a very nonlinear phonon operator. And these guys can change the state. Take 2 deuterons, turn them into helium if they come close together, and vice versa. Phonon coupling to dissipation channels is being taken here to be a completely standard dissipation model, although insofar as it's a standard dissipation model, some of the dissipation channels can be at high energy. So the model is a fairly general model. The question is can it apply to any of the anomalies that have been proposed or observed experimentally? The question is, can we explain heat and helium with it? Maybe, maybe not. But in all of the anomalies, the fast ion emission business within the framework of the model seems to be the one which is simplest. For example, if I have a fusion reaction, and if I couple one phonon indirectly to the phonon modes, and then express that one phonon to a dissipation channel, then energy conservation says I get a large energy transfer virtually to the lattice. Goes to the dissipation channel, I'm going to get 24 MeV in the final product. Now, the only dissipation channels of 24 MeV are nuclear channels, ejection of an alpha particle out of the nucleus or some such. So the one quantum version of this would correspond to fast ion emission, and if you assert that might be true, you find that the NRL results in the Colorado School of Mining results correspond to what you would expect from an essential assumption. And then the theory for the rate seems to be able to give numbers consistent with the experiment. To get heat or even before you need many phonons, you need one phonon per higher energy dissipation channel. But if I have 10,000 phonons and I express them kilovolt per phonon per dissipation channel, then I have a mechanism. Tritium would be the same approach. Wolff's induced radioactivity effect would correspond to about 71 phonons per channel, and then radioactivity channels about 350 kilovolts. Kasagi's three-body experiments, basically a deuteron comes in, and it seems to hit two deuterons together. The probability for which d10 to the minus 30 theoretically, or lower, experimentally is about 10 to the minus 6. And this overall theory would give deuterons coming together a significant fraction of the time. So in terms of applying to the anomalies, we're thinking about the possibility of having a unified theory now. Coherence is important. The model says nothing happens unless there's coherence. And by coherence, basically the interaction has to be the same at all sites. Whatever happens at one site for two deuterons has to be the same as what happens to another site. If all the sites uniformly interact with the lattice, then there's a possibility for n-squared effects. This is usually modeled using Dickey algebra with pseudo-spin operators, which are many particle operators. So this would correspond to one phonon mode interacting the same with deuterons at all sites. Now the only problem is, having said that, the basic interaction doesn't look the same at all sites. In fact, you can hardly imagine having an interaction looking more different at all sites. So you might say, well, this model is the canonical example of an incoherent model. Now, any operator should have a coherent piece to it. It should be made up of an incoherent piece and a coherent piece. The only question is how do you extract the coherent part of such an incoherent operator? There's no papers on how to do this, and we had a brainstorm that if a total operator with a coherent part and an incoherent part were applied repeatedly to a function, the part that would be coherent should come out, rise out of the noise after a large number of applications. At least that's the brainstorm. So if we operate many times, then maybe the result of it would be roughly the same as we operated with a coherent part many times. And if we do that, that would give us a coherent part. The interaction looks like this. Now, this turned out to be an approximate result. Having that bit of insight, I can go back and calculate using geometric arguments what the interaction is. So we've actually succeeded more or less getting an exact version of the interaction, the coherent part of the interaction, so we now have the coherent part in the proper form of the Dickey operators. And it depends on a collective phonon coordinate. Basically, the phonon coordinate is the one that at every site wants to bring two deuterons closer together, all at the same time. Retrospectively, it's obvious that that would be the collective coordinate, but it only took 8.5 years to find it. So this gives us a model now that we can begin to apply to fast ion emission. At NRL in 1990, George Chambers and Grabowski and Hubler did experiments where they saw 18 to 21 MeV alpha particles coming out of the palladium deuteride. And if we look at this mechanism, 24 MeV second order coupling of phonon modes coupling to palladium, in fact we get 18 to 21 MeV alpha particles coming out of the model. We take the basic model, simplified for the purpose of being presenting here. Two-level systems, single-mode oscillator, dissipation channel associated with alpha decay, coupling. We can use Fermi's golden rule to calculate reaction rate to get the matrix element. If we assume ground state dissipation system and phonons in the lattice and Dicke states, we can calculate the expression for the Fermi's golden rule. The point is that we've got a well-defined theory, we've got Fermi's golden rule. We can generate expressions for reaction rates, so we can evaluate the model, see how it works. What we find is a rate estimate when we make a lot of approximations, pretty good approximations. Rate estimates that look like this. We've got the overlap probability for two deuterons, number of deuteron pairs, Dicke coherence factor, number of palladium atoms. We've got nuclear interaction compared to the nuclear energy exchange. I'm assuming electrostatic Coulomb potential interaction with the alpha. And from this and this is dipole-dipole coupling. This factor is due to a lot of destructive interference in the two terms for the Fermi's golden rule, second order theory. Now, if you plug in numbers and evaluate this, you find that the numbers are low relative to what's needed to account for the experiments by something in the neighborhood of probably 5 to 10 orders of magnitude. Nevertheless, it is possible within this mechanism to pick numbers here and elsewhere to correspond to something you can measure. Just scratching out what's wrong. What's wrong is that describing the exchange of a 24 MeV photon with electrostatic interactions is probably inappropriate. You do a relativistic theory that breaks the cancellation. You get much bigger numbers. You apply the model to the data from Colorado School of Mines, Cecil data. Cecil sees deuterons around this energy, protons in the range of 12 MeV, helium-3 around 5 MeV. You get, out of the box, you get a spectrum of particles and energies which matches Cecil's data decently. Summary and conclusions. We've got a new model now that talks about interaction at close range between deuterons and the lattice. The strong force now is interpreted in terms of phonons, so you naturally get phonon nuclear coupling, as documented in a Phil Mag-B paper from 1999. Thinking about using the models to account for anomalies, fast ion emission is the simplest application of this kind of model. The coherent part of the nonlinear interaction is succeeded in extracting, I think, the first time anyone's extracted a coherent part from such a model. We've identified collective phonon coordinate that the system responds coherently to. And this collective phonon coordinate appears in many experiments to be the thing that needs to get things jump-started. The electronic flow or flux of deuterons through a material seems to be required. And that would be the collective phonon coordinate that we've described mathematically would respond to that kind of stimulation. We can analyze Fermi's golden rule quite rigorously. We've got a demonstration that the reaction rate goes like n squared is appropriate for a coherent system, and so forth. That I'm interested in seeing more experimental data for fast ion emission. Hopefully I can twist Mike's arm in the coming year to maybe do some of these types of experiments. Maybe others will.
That was the first time at all.
No, second.
That was the second time. You may have some minor there. I have a long time for questions. Okay, well, moving right along. We now have this is Tom Claytor, talk. McKubre a year ago said that he was a much younger man. Anyhow, Tom is actually about that.
Yes, Tom couldn't make it.
Sorry about that.
He asked me to give a Claytor impersonation, which I'm about to do. Tom Claytor, for the last 10 years at the Los Alamos National Laboratory, has been making tritium using a technique which defies explanation and is contrary to expectations. Now, you could easily dismiss this, except that Tom is using state-of-the-art equipment, and he is a man who has state-of-the-art knowledge of tritium. And in addition to that, as you might expect in a national laboratory, this work has been looked over with a fine-tooth comb. Many people have tried to find explanations and the way in which you might be making mistakes, and they have failed. The tritium that he's making results, presumably, from the DD reaction, and when that happens, it comes off normally with 1 MeV of energy. That's when it happens in plasma under conventional conditions. This tritium results in tritium that has no energy, or very little energy. The amount he's making is in a neighborhood of 2 times 10 to the 10th atoms. So it's a very small amount, but you have to remember that the amount of palladium that he's using is only 100 milligrams, and so it's correspondingly small. He has explored a variety of materials to try to find ones that produce this effect routinely, and that's been a problem. The ones in red are ones that are batches that have produced excess energy. And there are certain batches in the pure palladium that has done this, but that isn't really pure, and the effort is to try to add impurities that might enhance the effect, and this is why these alloys have been explored. Certain of the alloys have a better, do produce energy, and some produce none whatsoever. The alloys that produce more routinely are ones that contain boron. He's also tried a number of other metals with no success. The technique involves subjecting the material to a plasma discharge. A voltage between 1500 and 2500 volts is placed in a partial pressure of deuterium gas, causing a current of about 2 amperes to flow for a microsecond. And then this is repeated on a millisecond basis. So the piece of palladium gets a very strong jolt of deuterium for a very short period of time. The deuterium is then pumped through this loop, and any tritium is detected by the Femtotech tritium gauge, which measures tritium by virtue of the ion current produced from this radioactive disintegration. In addition to that, he is able to pump out this deuterium, react it with water, with oxygen, convert it to water, heavy water, and collect it. And then that heavy water is then analyzed for tritium in the conventional way using scintillation counting. The two techniques agree very, very well, within 20% of one another. So there's no doubt that he's making tritium. You might have a doubt as to where it's coming from, but he is making tritium. Or he's detecting tritium, I should say. The discharge looks like this. The challenge is to cause the discharge to occur just between the pieces of metal and not extend into the insulated region. He's tried a number of different designs, and this has been perfected over the years, such that he can define exactly where this discharge is going to take place. And that part of the effect is under pretty good control. The result of the discharge is to produce a very strange structure on the surface of the cathode. And this morphology appears whether it makes tritium or not, but it's characteristic of the region where any reaction is going to occur. I'll give you some idea of the kind of data that this produces. Here's the tritium concentration in nanocuries per liter against time. The material have generally 3 different characteristics. They either go right along this line, which is 0, or they tend to go a little bit below the line, or they go above the line. In other words, nature gives you every possibility. And this is a sample that's not particularly very good, but you can see that there is a slight tendency for it to rise above the line. A few samples show nothing. A better example is this collection. You can see most of them did nothing. A few went below the line slightly. One here goes along the line. And then there's some here that are beginning to show some light in them. These peaks are caused by changes in room temperature that occurred during that particular run. And then we get to the piece de resistance. Here we have a sample that's really quite good. It's showing a steady increase in tritium with time. Here's hydrogen. He does run ordinary hydrogen and finds nothing happens. It just stays essentially on zero. This particular sample, various things happen that are too complex to talk about, having to do with the nature of the plasma. But when the plasma was turned off, such that those effects did not impact the level of tritium was at this point. So in reality, it rose like this. And that's considered a very good sample. The presence of neutrons, emitted neutrons are looked for, and also radioactivity that has gamma emission in the palladium after the study. Neutrons are not detected. That indicates that the tritium is being produced without any energy, otherwise it would have produced 14 MeV neutrons by virtue of a DT fusion reaction. That does not occur. And there's no gamma activity other than background in the material after the run. Well, what's going on here? There's a number of possibilities. If you have a skeptical bent, which most people do, are the results artifacts? Well, bent have artifacts, and the process of discovering what's going on there, Tom's probably become the world expert in bent technology and behavior. It does have artifacts, but he pretty much understands what those are and can eliminate them. The system can be contaminated. That is, tritium can be coming out of the walls of the stainless steel tubing or whatever. Yes, tritium does get hung up in the system. Yes, it has to be baked out. It has to be gotten out by various ways, but it can be removed. And by virtue of the Pententech looking at this in real time, you can tell that contamination has been removed. Spot contamination of palladium. You can't argue that it's total contamination because it only happens in a few separate pieces of palladium, so it has to be spots. So you have to argue that whatever contamination is in there, it happens by random chance to occur in a particular piece of palladium he has to pick up. He's studied palladium quite extensively, trying to determine if there is any, in fact, contamination within palladium, and there is none. I mean, that was a red herring that was thrown out early in the field. Palladium is not contaminated with tritium.
Yeah, that came from the concept that a lot of the palladium has been involved in electrolysis separation of tritium.
Yeah, it was a plausible suggestion, but it turns out to be absolutely false.
Yeah.
And that also applies to palladium that people have used in electrolytic cells and in other environments where tritium has also been seen. Summary of the results. Palladium alloys show different amounts of tritium generation. Once again, it's demonstrated, as it has been in all the other studies, that it is material specific. It really matters as to the nature of the cathode. He finds this, everybody finds this. The batch-to-batch variability is still a problem, and that's particularly a problem with palladium because palladium is very inhomogeneous in all its properties anyway. Forget about cold fusion. Palladium is a nasty material to work with. It really, it's very difficult to get it uniform. There's no identified gamma seen in post-test, and the in-situ loading measurements reveal that achieving moderate loading with the plasma technique is difficult. In other words, the average composition of the samples are very low, maybe around 0.5. The D to PD ratio is maybe about 0.5. But obviously, during the microsecond that this is being subjected to 2 amps of ion current, the surface has achieved a very high composition. And that seems to be a prerequisite for these things to work in all the applications to which palladium has been placed. All right, that's pretty much what he had to say.
Okay.
What were the diameters of those rods?
Well, they're in the neighborhood of a few mils, a few. Yeah, well, less than a half a millimeter.
Less than half.
Yeah, they're much less than half a millimeter. More like in the 10th millimeter range.
There,
And these jagged curves that you show, I understand are the meaning. Are these continuous illustrations of events or are they data points that you connect with the...
This is continuous. The Femtotech puts out a signal that is continuous in the computer. In other words, it takes a reading every part of the second.
It depends on those pulses. And reading per pulse.
Oh, no, not for reading per pulse. The pulses are a microsecond long.
Duration, yeah.
100 millisecond between them. And those are coming regularly. The Femtotech then puts out a signal. It's essentially a DC signal that then is put out as on a chart.
Does Tom really see boron in the palladium system as a very, very central element? It seems boron is a common element.
no miles.
Well, boron is not the smoking gun. I mean, there's lots of boron samples that produce absolutely nothing. But boron, the probability of it working with boron in it is higher than the probability of it working without boron.
And Dr. Rath at NRL suggested that what the boron could help to do is to create lots of small crystals, effectively, which may actually be part of the reason. Well, that was the reason that, in fact, Imam at NRL introduced that based on that suggestion and designed it explicitly with that in mind.
Well, just to add to that, boron does lots of different things to palladium.
It does.
It increases the ability for it to load, for one thing. Tom Passel argues that it is involved in the nuclear reactions itself. It changes the hardness of the palladium such that it would not crack so readily, and that's a prerequisite for this work.
Yeah, but there are lots of different phase configurations of them, even dependent upon temperature. Yeah, Peter, correct.
Actually, the relative absence of neutrons basically means that tritium has to be worn stationary.
Right.
Mainly, if you go back and calculate what's the maximum possible energy we could have, it's less than something like 8 kilowatts. So the question is, you have a Canadian flag. Los Alamos becoming a Canadian?
Those were slides that we didn't expect anybody to notice. We're very observant, but they were left over on the slides.
The same question, I just wondered if,
okay.
last data you showed was 1998. Is he still doing anything?
Yes, he's still working, but frustratingly slow. The problem at Los Alamos is very interesting. People at the level that are aware of what he's doing are very supportive. And the further you get away from that level, in other words, the greater the ignorant content of the people, the more skepticism you have.
That's a common.
And at the high levels where the money is doled out, the skepticism is fairly high, so he has a problem.
I'm cutting him off because we got to keep the schedule, of course. The next talk is probably one of the more, well, they're all important, but McKubre is done seminal work.
This would make it impressively unique.
Mike McKubre is going to talk right now. And getting into his time.
If I'd have remembered that the talk was to be 10 minutes, I would never have proposed such a grandiose title, which I obviously can't do justice to. And today I'm going to talk just about one point, measurements to correlate the appearance of heat and helium-4, measurements performed in our laboratory over a series of years, and 3 experiments in particular. First time we worked on the heat-helium problem was really in response to the publications of Mel Miles, who was here in the audience today, who performed his experiments in glass, and the idea was can we replicate his experiments in more robustly sealed metal vessels? We operated the cells in the same way that Mel and Van Bush had operated them at China Lake, that is open cell experiments, self-purging for helium-4, using a liquid nitrogen blanket to exclude helium-4 from the environment. Highly accurate integral boundary Seebeck calorimeter that Van Bush had developed, a very nice machine, using SRI online real-time data acquisition and control. And this work, in fact, was published recently in the report that cost you $20,000 and isn't worth it.
You can say that now they're not funding.
This was the result that Ben achieved, and basically there are a number of, here we have the measured helium in parts per billion. Note the billion. The helium is diluted by the electrolysis off gases, the deuterium and oxygen gases evolving from the cell. So any helium that we might expect to see is diluted by the evolving gases. This is good news and bad news. Essentially, in a large number of experiments, we saw no heat and we saw no helium-4. In 3 experiments, we observed what we believed to be statistically significant excess heat measurements and did not see within the detection limits helium. In 3 experiments that we performed, we found some time correlation between the appearance of helium-4 and the appearance of excess heat. And if I draw a regression line through these 3 data points, the 3 non-zero data points, we get helium-4 to excess power, excess heat correlation, which is something like 76% of the expectation value if you're expecting to yield 23.82 MeV per helium-4 atom. So this is an initial experiment. It confirmed the result that Mel, Miles, and Van Bush had performed, certainly consistent with the idea that we have a reaction D plus D to helium-4 yielding 24 MeV to the lattice. Helium was only observed when excess power was present, and the concerns with that particular experiment, small absolute values of both the excess power and the helium measurement, measuring helium at the parts per billion level, in order to achieve ambient levels of helium-4, 5.22 parts per million, we'd have to achieve an excess power of something like 1,000 times the input electrolysis power. This is a level that we have never achieved in our experiments. The other concern is this missing helium. We didn't get as much helium as one would expect for the postulated reaction, and in some cases we didn't see helium at all. So perhaps the helium is hiding out or it's delayed in some way. This is a reference to Mel's work over the years from 1991 to 1994, so a fairly significant amount of work has been published on heat-helium correlation, other than the work done at SRI. Second series of experiments, instead of electrolysis, we've tried to do something much more simple. Simple gas loading. Deuterium gas pressurized and heated, enclosed and sealed metal vessels. We put the deuterium gas, exposed it to commercial carbon catalyst, which has between 0.4 and 0.5% palladium in very finely dispersed islands on top of the carbon support, pressurized in the realm of 1 to 5 atmospheres gauge, operating within this temperature regime in a non-isothermal condition. In fact, if you operate this experiment isothermally, you get no interesting results. Data acquisition. In this case, the first time ever attempted in this field, I think, online monitoring for helium-4 with a mass spectrometer which is capable of resolving the mass 4 peaks of D2 and helium-4. And correlated calorimetry. This experiment was performed in this basic geometry. 2 cells. Let's imagine that one of them is a foreground cell and one of them is a blank cell. A blank cell in some cases containing hydrogen, in some cases containing inactive catalyst. But basically we have stainless steel vessels. Machined, in fact, to include a common-flat seal. We have a thermal well integral to this device. We have one thermocouple down in the catalyst bed, one thermocouple here up in the gas phase. The black here is the carbon catalyst, and it's heated by a helically wound heater on the outside surface of the cell, that any heat flow is from the heater into the cell and up, out through the top of the cell. It's all put inside a stainless steel dewar and packed in thermal insulation. What we're trying to do is observe with this capillary gas line if we're producing helium-4 in the presence of D2. This is the gas manifold. Basically, that line goes to one or other of these ports on the gas manifold. We have sample gases for calibrating the mass spectrometer. We also take periodic measurements of the room air to determine the helium-4 level in the room air, which is 5.22 parts per million. I don't have time to dwell on this, but basically this is the mass 4 peak of helium-4. This is the mass 4 peak of deuterium, which we normally don't see because we use a liquid nitrogen called carbon trap to scrub out the D2 without affecting the helium-4. But for the purpose of convincing one that the mass 4 peak that you are in fact observing is helium-4, it's sometimes convenient to let through some D2. So we see both the peaks and can be certain that the peak that you're looking at is helium-4. Series of experiments. In that particular geometry, more experiments have been done. Basically, the experiments fall into, I think there are 16 experiments in this series. They fall into 3 categories. First category is nothing at all happens. The helium-4 level does not change with time. The vessels are effectively sealed against ambient invasion of helium-4. Sits there on the baseline, nothing happens. Second group shows this sort of exponential rise in helium-4 with a very long time constant, something like 30 days here, which are interesting, but they're slightly tedious. More interesting experiments show no increase in helium-4 for a period of time, a rather rapid increase, and then a slight delay. You can see my time is passing. If we look at the correlation between those results which show the rapid rise in helium-4 and the excess power that we observe, here we have one particular example, helium-4 at a constant baseline level. This is the background level of helium-4 in the experiment. An abrupt increase and an abrupt increase. The green and blue lines are the calorimetric results obtained in heat flow calorimetry calculated in 2 different phases. It's quite clear by eyeballing this that the correlation between the appearance of helium-4 and the appearance of excess energy is quite strong. There's a correlation coefficient, I think it's 0.92. So we're confident here that the heat is being produced at the same time as the helium-4. And the question now is there quantitative correlation? This result shows quantification, the estimated energy presuming, this is the measured energy, this is the increased helium, and if you look at the Q value for the helium yield versus the heat yield, we find values of 31 plus or minus 13 or 32 plus or minus 30 MeV per helium-4 atom. So the expectation value of 24 is certainly within the uncertainty, but I think that the answer is actually closer to 24, and that we're underestimating the helium for the same reason as we were in Dan Bush's experiments, that there's some sort of hideout of helium-4. I'm going to skip through a bunch of slides which are somewhat relevant. We can get back to them later, perhaps. Just addressing the point of helium-4 hideout, is this possible, is it reasonable, does it occur? This is one of our earlier experiments presented at ICCF 5. In fact, here we have an excess power result achieving something like 400 milliwatts of excess power. The green line, for some of you who will remember this, is my prediction value for excess power based upon various terms that we've measured. Just concentrate for the moment on this excess power curve, and I'm going to integrate it to predict a helium-4 level in this metal closed experiment, M4. We performed the experiment. So that this blue curve here is the expected integrated value of helium-4 in that cell if we convert the excess power that we have observed to a helium concentration with this 23.82 AeV per helium atom number. So our expectation value for helium-4 at the time that it was first sampled is here. Our observation is this value. So we observed something like 62% of the expected helium-4, which was interesting and nice and made me happy, but not completely happy. We waited for a little time, and it turned out that the helium-4 value increased in that vessel with time, suggesting that helium-4 was being released slowly from some part of the system, so that after a week we had increased the value from 62 to 69%. To make a long story short, what I did was then undertook a series of exercises of the palladium cathode, making it an anode and making it a cathode, putting hydrogen into it and taking hydrogen out of it, and changing its temperature with the idea that we could somehow dislodge superficial helium-4 from the palladium lattice, make it available to the gas phase for analysis. And after that week of exercise, we took another helium sample and found 104 plus or minus 10% of the expectation value of helium-4. I'll put my conclusion slides up since you're not going to ask questions. But it seems perfectly plausible that the reaction that we're looking for is in fact D plus D to helium-4. That not all of the helium is released immediately, that you have to do some work to release it, but that if you exercise the palladium lattice appropriately, you can dislodge sufficient helium to make a quantum.
Also produce excess energy. This has also been seen by John Dash at Portland State and also in France by Longshot. So I'm not the only one, but the importance of this particular study is twofold. One is that it's the first study that has been made available in total on the internet. You can download a paper describing the work, and you can also download all of the primary data. And so you can take your time and figure out what I did wrong, where the errors are, anything you want to do. And you just need to click on this website that's noted there. And you will get a paper, and you will also get a response. After this was put on, a number of people raised questions, and then I went back and answered those questions. And so, go ahead. Before I can convince you that what I'm going to show you is real, I have to convince you that the calorimeter is capable of measuring what I'm claiming. This calorimeter is a stirred calorimeter. It's a combination of isoparabolic and prototype calorimeter. I measure the heat generated by the changing water temperature flowing through a jacket, and also the delta T across the cell wall. It contains a recombiner, contains several places where the temperature is measured, and it contains a heater for calibration purposes. It has a stability of about 50 milliwatts over a long period of time. This shows the calibration curve. This is applied power against delta J, which is the temperature difference between the inlet and the outlet water temperature times the flow rate. You'll notice several things. It's nearly 2% of ideal. In other words, only 2% of the energy that's being produced is lost. It's within almost 98% of ideal. And there's very little difference between the calibration obtained from the heater and from electrolysis. They both give the same value. Well, let's show the time history of the sample. This particular piece of platinum was placed in the calorimeter after it was calibrated, as I showed you earlier, and a sweep was brought. Now, a sweep consists of changing the applied current in steps, allowing time for the calorimeter to reach equilibrium, and then 5 points are taken, and then it goes to the next step, goes up, and then it goes back down. So that's a sweep. And you see at the highest current, which is 3 amperes, it's about 750 milliwatts that it's producing in excess. This is excess power. Well, then I put on 5 amps, got the expected amount, put on 1 amp, got the expected amount, it stayed constant, went to 1.5 amps, and after a delay, it started decaying. And it disappeared. The sweep was done here, and there was very little energy left, and it was held for a while at a 0.5 amp, nothing. It had gone dead. Now, of course, this is known as great disturbance. So I turned the current off at this point for a short time, and turned it back on, and lo and behold, when 0.5 amp was applied, it had become alive again. I got excess energy. Now the sweep shows the same effect as before. This is 0.5 amp, 3/4 amp, 1 amp, 1.5 amp. Uh-oh. After a delay, it started decaying again. And even though it was at lower currents during that time, whatever was done here was fairly permanent. And it decayed down to 0. So again, power was turned off. And 0.5 amp was applied. Now there was a 0 offset here that shifted slightly, so we have to now make a comparison to this new line. So we have the excess. Went back down to 1/10 of an ampere, where it produces nothing, and that's a 0 point. Went up to 0.5 amp, and then another sweep, there it is, and then there's a partial sweep. At that point, the sample was taken out, and a dead piece of platinum was put in, and it was recalibrated. So let's look at these sweeps. They're rather interesting. This is the excess power against applied current. This is the first sweep. Now during the first sweep, nothing happened. As the current went up, there was no change, and then suddenly it took off. At the same time, the isoparabolic, that is the temperature delta T across the wall, also showed excess energy. These are 2 independent measurements. On the way back down, it stayed high. Follow on down. Let's look at all of the sweeps. These are all the sweeps superimposed. In addition, the calibration before and after. This is the platinum, dead platinum. Before and after showed very good agreement, and this is the various sweeps. It shows a linear variation with current extrapolating to 0. This is in contrast to the behavior of palladium. Palladium typically has a critical onset. You have to go above a particular current before you get any excess energy. I believe the reason for that is that in the case of palladium, there's a loss into the palladium from the surface, and that has to be overcome. You have to put on extra input, so to speak, to offset that loss. Whereas in platinum, there is no loss into the interior. Platinum does not take up hydrogen very well, and it doesn't diffuse it very well compared to palladium. And so one does not have that loss to offset, and as a result, you get this behavior. All right, so then the sample was put back in after having done that calibration. 0.5 amp, a sweep, oh, there it is. Another 0.5 amp, and then I held it at 3 amps for a while, and it died again, actually. Did a deloading at this point, oh, but it didn't come back on. 0.5 amp, there wasn't anything there after that. So obviously, that was too much for it. I could not repair it just by simply turning the current off. So I took it out and boiled it in water. Put it back in. Oh, there it is again. Another sweep, another sweep, another sweep.